Welcome, everybody, once more to the official IAU G2 conference series. As usual, this is about massive stars, and today is my real pleasure to introduce Sophie Rosu, presently a postdoc fellow at the Observatoire de Genève in Switzerland. Sophie did her PhD thesis at the University of Liège, finishing in August 2022. The title of her thesis was very close to the main topic she will be talking about today, Apsidal motion in massive binaries. And after that, she moved for a first postdoc to the KTH Royal Institute of Technology in Stockholm, Sweden, where she was developing a detailed study of the Jetta and the rings of supernova 1987A. And then in 2025, she started a second postdoc, this time joining the stellar evolution group at the Observatoire de Genève, led by Sylvia Ekstrom. And in this case, she's focusing in using the axial motion in massive binaries to prove the interiors of stars with the stellar evolution code GENEC. Her expertise is mostly observational and modeling of massive binaries, but she also has interest in multiple systems and also obviously the supernova she was studying in her previous postdoc. And I also know from own expertise that she has a very special recipe to cook waffles from Liège. So on behalf of the IAU G2 organizing committee, I want to warmly thank everybody for joining us today, and especially to Sophie for accepting our invitation to deliver this seminar. So whenever you want, Sophie, the floor is yours.
Thank you very much, Sergio, for this very nice introduction and for this invitation. So as Sergio said, well, today I will talk about a topic that is really close to my heart, and I would like to I give myself 45 minutes to convince you of the beauty of K2 and the powerful method of Apsidal motion to probe interiors of massive binaries. But before I start, I would like to thank my two very close collaborators, Luca and Silvia, for their input on this work and our collaboration. So because I have 45 minutes, I can introduce the topic properly, and I will do so that we all start with the same basics. So here I would like to show in case of point-like particle in a binary system, we have a primary star here that is denoted by P that is orbiting on the orbital plane in yellow. And if we only have point-like particle, the only thing that is going to change in this orbit is the true anomaly, so the position of the primary star on its orbit. But I'm not going to tell you anything new if I tell you that the stars have a three-dimensional shape and that there are tidal interactions that occur between the two stars. So there is an exchange of angular momentum, and the stellar deformation are responsible for the gravitational potential of the star to be non-spherically symmetric anymore. And the most prominent manifestation of this effect is the slow precession of the line of Apsidal. So this is depicted here. So this is basically omega, the longitude of periastron that is going to change with time. This is usually a very slow motion, so a few degrees per year only. But I want to stress, and this is the very first important key point of my presentation, that this is clearly a non-Keplerian movement. So it happens because the stars have 3D shapes. There is a general relativistic contribution to this motion. However, at least for the system I'm studying, this contribution is much smaller, around 10%-ish. So this motion is small. Do we care? Do we have to care about it? Can we measure it? And if yes, how? Well, yes, we can measure it, of course. And here I want to show you a plot where you see the Apsidal motion period as a function of the orbital period of the system for different binaries. So here only the primaries are depicted and color-coded by their mass. And you can see a general trend of the Apsidal motion period increasing with the orbital period in the system, which is expected because if you have a longer orbital period, then the stars are further away, the tides are less efficient, and the motion is smaller. And another thing that you can also see here is that all these more massive stars, they also have a shorter apsidal motion period for the same orbital period because they are more massive and the tides are more efficient also. So these are all individual studies, and there are so many that I couldn't quote all of them. But here I would like to quote two studies that were, to my point of view, very tremendous because they studied not in the galaxy, but the LMC and the SMC. They studied a bunch of binaries and derived their apsidal motion periods. So I think this field is growing, and there are more and more evidence that this can be measured. And how it can be measured? Well, my answer will depend whether we have a double-line spectroscopic binary or an eclipsing binary. So in the former case, what we can do is first remember the radial velocity equations. I'm not going to teach you anything, but I want to show you that those radial velocities depend on omega here. And if you account for a linear change of omega with time, then fitting those radial velocities will allow you to get this apsidal motion rate. In practice, what you need is long time span of the observation because this is a slow motion, so you really need decades of observation usually. But once you have those decades of observation, then you can get something that is very accurate. And here I want to show you an example on my benchmark favorite binary star that you're going to hear about during the World Talk. And what you can see between the first and the last observation that are taken about 70 years apart, you can clearly see change of morphology of the radial velocities curves here that are attributable to this apsidal motion. If we have an eclipsing binary, then what we can do is to use the light curves, of course, and I'm going to show you how we can do so. And here to illustrate it, I computed theoretical light curve for different values of omega for still the same binary system. And I have to say that this is a twin system, which means that the two stars have the same stellar properties, including the effective temperature. So the change in depth of the eclipses that you see here is not due to a change in effective temperature, but this is due to the eccentricity of the system and also the change of omega, as you can see in the light curves. So for this light curve, omega ranges between 0 and 160 degrees. And for these values of omega, the primary eclipse happens close to periastron passage when the two stars are the closest. So this is why this eclipse is deeper than the secondary eclipse, because the depth of the eclipse changes as a function of the orbital separation at conjunction phase. And this is why also you will observe that depending on the value of omega, so depending on also the orientation of your ellipse with respect to your line of sight, you will have changes of the depth of the eclipse, but also the phase of the eclipse, because the two eclipses do not have to happen at phase 0 and 0.5 all the time. So you can see from that if you fit the light curves or if you fit the time of minima of the eclipses, then you will get an apsidal motion rate. Usually this technique is a bit more easy to apply because with the test data that we have now, a few times of minima are sufficient to get very accurate apsidal motion rate. This is illustrated here. So this is a study of Baroque 2021. And you can see that they got very small apsidal motion rate, but also very accurate one based on their time of minima of the eclipses. So secondary minus primary. Of course, if you have a spectroscopic plus eclipsing binary, this is the wonderful world because you can use all the data sets to get a consistent apsidal motion rate in the system. So this is illustrated here also. So you have the adjustment of the radial velocity curves in blue. The different point, black and pink and red ones are the adjustment of the light curves. And in green, this is a global fit with Phoebe of all the data at the same time. And you can observe that first, all the data sets are consistent, but also you can get with the global fit something that is extremely accurate. I want to show you two other examples. This one is another one that I studied. You have omega as a function of time, the radial velocities again in blue, the adjustment of the light curve in pink. And on the right-hand side, you have the phase difference between the two eclipses. You have what you get from the time of minima in pink and what you expect from the radial velocities. And you can see that everything is consistent. Here we had less light curve than radial velocities, so the radial velocities were really useful in this case. And the last one is a system where the apsidal motion rate is quite large, actually, with 15 degrees per year. And you can observe here the adjustment of the time of minima. And on the right-hand side, you have in green what we expect from the time of minima, and the different dot, the adjustment of the light curves. Those results are also consistent with the radial velocities, but I just didn't show it here. So when I talk about apsidal motion, I like to quote Claret, because then I'm not the one responsible to say this sentence, that one of the most reliable means of studying the stellar interior is through the apsidal motion in double-line eclipsing binary system. So I want, in the further slide, I want to show you how he is right and how we can probe the interior of stars using the apsidal motion. But for that, we will have to go through a few equations first. So first, the apsidal motion is, as I told you at the beginning of the presentation, the sum of the Newtonian contribution and general relativistic contribution. The latter one is very simple. It depends on the orbital period, on the mass of the star, and the eccentricity. And you can basically, if you have, and that's what we're going to assume for now, a double-line eclipsing binary, you can get all these quantities on the right-hand side from observations. The Newtonian contribution takes into account two things: the tidal deformations, but also the intrinsic stellar rotation. And it depends on function of the eccentricity, F and G, but also on the radii of the star, the semi-major axis, the mass ratio Q, the rotational period, and the orbital period, of course. So again, all the quantities on the right-hand side can be derived from observations, but the K2. And the K2 is formally the internal stellar structure constant. So let's keep it K2. Very simple algebraic function of eta2, which is itself the solution evaluated at the stellar surface of the Clairaut-Rado differential equation. So we integrate this equation from the center to the external layer of the star. So here is r, the distance from the center. And you can see that it also depends on the ratio between the density in a shell at distance r from the center of the star divided by the mean density in a sphere of radius r. So at first sight, what K2 tells us about, it tells us about the density stratification inside the star. And this quantity decreases with time as the star evolves and as its core contracts and its envelope expand. So here there are different models. It doesn't matter which models are, but I want to show you that K2 decreases as a function of decreasing hydrogen mass fraction in the core, but also decreases as a function of the increasing radius. So another thing also that is very important, and that's gonna be important for the rest of the presentation, is that here you can see that K2 will mostly depend on this region here. And this region is the border between the convective core and the radiative envelope. So the value of K2 will change as a function of the density stratification inside the star, but it's going to be very sensitive to the border between the core and the envelope. So when we confront theory to observations, there are different things that we can observe. Here is the study of Claret 21, where they studied 27 double-line eclipsing binaries with different ranges of mass. So you have the observational apsidal motion rate as a function of the theoretical. You can see that it looks like it does agree, except from one peculiar system. If you look at the K2 observational versus theoretical, is also good. But when you do a close-in view here, and you have the K2 observational minus the theoretical as a function of r here, which is the radius of the star divided by the semi-major axis, you can see that for the smallest value of r, this is consistent with theory and observation are consistent. But when we go to the larger value of r, it is marginally consistent, I would say, because most of the observational K2 seem to be lower than the theoretical value. And this is especially true for EM car here, but this is also true for other systems. And it turns out that the system for which there are the largest discrepancies between observational and theoretical K2 are those where you can find the most massive stars. So it turns out, I just show you one study here, but there are more studies. It turns out that for lower and intermediate mass star, there is no apparent problem when you model the star, but when you go to the most massive stars, it starts to be that the K2 observational and theoretical do not agree within each others. And I want to illustrate that with two systems I have studied to really understand what's happening. So let's go back to my favorite binary here. You have the properties, the HR diagram, and the position of the star here in the HR diagram. So I computed this blue stellar evolution track with clay with an overshooting of 0.2. And I have to tell you that I use a minimization technique to find the best fit models in terms of mass, radius, and position in the HR diagram. And this is the track that corresponds to my best fit. So definitely it is not best fitting anything here, but that's what I could get. Then what I did is that I put turbulent diffusion inside the model. So it's basically more mixing inside the models. And now you see that you have a track that perfectly passes through the observation. And here it has the proper mass and radius. But if we look now at the K2 value, here the green dot is the model that has the correct value of K2. And as K2 is decreasing with time, then it means that when you are here just at the position of observed effective temperature and luminosity, you have a too high K2, which means that the model has a too low density contrast between the core and the external layers. And to overcome this problem, we had to put some more turbulent diffusion, so more mixing inside the models. And we got this orange dot that best fit not only the mass and the radius and the position in the HR diagram, but also the apsidal motion in the system. So this is a very important result because it already shows you that if we didn't have the apsidal motion rate, we would have thought that our green model is perfect, but it is not, and we need more mixing. So you may say, okay, this is just one system, but I have other system, and I want to show you another system where here again in green, this is our best fit track in terms of position in the HR diagram, mass and radius. And you can see that the K2 is not well reproduced. So we have here the models that should have the proper K2. And we need to put more mixing, much more mixing. And we have this star in orange there. That is our best fit. And this is clearly not sufficient. It's marginally best fit. It is better, but it's not the solution yet. So with that, I think I have so far convinced you that for the most massive star, we can observe this K2 discrepancy where the K2 of the models are systematically larger than the observational K2 for the massive stars. So the models predict stars which have a too low density contrast, while the observation, from the observation, you expect that the star have a core that is more contracted and an envelope that is more extended. But these were preliminary tests, and now I'm investigating that with better stellar evolution models that include better physics, that include the rotation of the stars, but also binary effect and so on. So that is what I would like to describe now. So first, let's go back to my favorite twin system here. So you have the different properties of the stars and the orbital parameter. And I have to stress that all the properties are important, but some are more important than others. And these are the K2, of course, because this is the technique that we're applying, but also the radius, because if we go back to the equation of the Newtonian apsidal motion rate here, which is simplified in the case of a twin system, you have here dependence on the radius to the power 5. And as you can see here, the observational determination of the radius is accurate at 1%, which means that basically if you get this radius wrong in the stellar evolution models, then there is nothing you can really trust in your models. Because if you change a tiny bit the radius to the power 5, it is a very big change and it has repercussion on the K2. So for now, I know it's very not conventional, but you're gonna see all my plot quantity as a function of the radius, because I really want my model to reproduce this radius of the star. So let's look a bit at the input physics I put in the GENEC models computed. So we have two schemes for the angular momentum transport. We have the advector diffusive scheme, which sets the star on a differential rotation structure. And we can also, additionally, if we want to, put magnetism into the model, and then we have a diffusive scheme. We have single and binary models, and the binary models include the dynamical tides, but also the equilibrium tide of small subsurface convective zones. And if you want to know more about this new version of the binary models, then I direct you to the paper of Luca that has been accepted 2 weeks ago, where everything is explained about the binary physics that we have. Then we also include the mass loss rate of Krichka 2024 because it appears to be the one that best reproduces observed stars in this range of temperature. We have the NAC2 reaction rates. For the metallicity, we adopted something that is a little bit supersolar because this is what is expected for the cluster where this binary is belonging to. And for the helium initial abundance, there are studies that say it should be supersolar or the subsolar. So we adopted something solar, and we don't really know actually the helium initial abundance. And then the methodology was that I compute several tracks, and I adopted the initial mass of the star in such a way that when the star reaches the observed radius, it has the observed mass. For the initial velocity, I did the same for the single star models, which means that I put as an initial velocity for the stars the value in such a way that when it reached the observed radius, I have the surface observed surface velocity. And for the binary model, I did initialize the system synchronized. And for the overshooting, I adopted value between 0.5 and 1.0. So please don't run away because you see those very high values. This is supported by different studies, but to not disturb the flow of this talk, I will come back to those studies later. But I would like to already quote the study of Scott 2021, where here they expected for a 30 solar masses star to have an overshooting of 0.8. So let's start with the single star models first. So you have the different quantities that I told you they are shown as a function of the radius. The plain line are the advector diffusive models and the dotted line are the magnetic models. And when you go from blue to green, you increase the overshooting. And what you can definitely see on this plot is that you observe this K2 discrepancy. It is extremely difficult to reproduce the K2 of the star unless you increase the overshooting. But even with that, it's kind of okay for the advector diffusive model, but for the magnetic models, it's not as good. So why do we need this large overshooting to better reproduce the properties of the star? It sounds maybe a bit counterintuitive at first sight because if we want to decrease the K2, it means that you have a more contracted core and a more extended envelope. But this overshooting is actually extended, in a way, your convective core. So to understand that, let me walk you through this. So if you have a larger overshooting, you have a larger convective core, and you bring more fuel for burning, and you extend the main sequence lifetime. So far, I think it's good. But then it also means that when you arrive to the observed radius here, you also have an older age if you have a larger overshooting, which means that before reaching this radius, the star had more time to evolve and so more time to contract its core and extend its envelope. And this is why we get this smaller K2. But as Danny would say, there is one physics that is missing, and this is the binarity. So what happens if we have binary models? This is shown on the right-hand side. And you can see that, well, it's even worse. So not only now we cannot reproduce the K2 at all, but also we start to observe some difficulties to reproduce the effective temperature and luminosity of the stars. But one thing that should catch your attention looking at those figures is how the surface velocity is different between the single and the binary models. So it is quite important. So let me, don't take me wrong here, But if the single star models are apparently better to reproduce the properties of the star, this is by chance. This is because we ask them to do that. We choose the initial velocity in such a way that it has the proper surface velocity when we observe it now as the proper radius. But as you can see in this plot, the angular surface velocity of a single star is decreasing with time um, as the star is evolved, while its radius is increasing with time. And so in this case, you observe that the surface velocity is almost constant over time. But the star in reality has a companion, so its angular surface velocity is not a free parameter, but it is fixed by the orbital motion and by the companion. And actually, we observe that the binary is pseudo-synchronized. So we have here omega in green that is roughly constant over time. But the radius of the star is still increasing, so is the surface velocity. And so when you observe it now, right here, you can see that the star has the proper surface velocity. But throughout its evolution, it has had a much less, a much smaller surface angular velocity. And so it has much less mixing than the single star counterpart. So this is why when we reach the proper radius, the K2 is larger in the binary model. So the conclusion here is certainly not that the single star model are better, but the conclusion is that the binary models are the way to go. It's extremely important to take into account the binarity in the models, but then there is definitely something that is missing. So I have investigated a few things to see what could be the reason why we cannot reproduce this K2 in those stars. So first, we have some freedom on the metallicity. We have some error bars, so let's look at it. Here we go from the blue to the pink track, and you see that when you increase the metallicity, you go down in K2 here, but you also decrease a bit the effective temperature, yet the effect is very limited, and it doesn't solve our problem at all. So that's not the reason. Could it be the helium initial abundance that is not really observationally constrained? You can see here that when you increase it, so you go from purple to green and then blue, green, ocean green-ish, you see that you decrease the K2 and you also get back to property effective temperature. So it seems to be better, but still you don't reproduce the K2 and still I have increased by a large amount the helium. So even if the helium initial abundance seems to be a bit different than solar, it's definitely not going to be that high. So it doesn't seem to be the right solution. Could it be the mass loss rate? We know that, well, there are different prescriptions and so on. This is still matter of debate. And we know that the winds are clamp. And if the clamping starts close to the photosphere of the star, then it turns out that the theoretical mass loss rate are underestimated by a certain factor that is roughly 2. So what I did is that I multiplied the critical mass loss rate by 1.8. And here we move on from the pink to the blue track. And what you can see is that, well, first we had to start the initial mass of the star a bit higher because the mass loss rate is higher. So we have started to have a bit higher and effective temperature and bolometric luminosity. The difference is not really significant. But the thing here is that you see that the K2 is not changing at all. And why is it so? Well, because the star initially starts as being more massive, so its K2 will decrease faster, but it will also reach, the proper radius here, the observed radius, faster. And so it doesn't have the time to evolve as much as a star with a smaller mass loss rate. And so the density contrast is not as pronounced, and you have this balancing effect on the K2. And this is why you see no difference. So the conclusion is that even if the mass loss rate is underestimated, here we do not really care. And I think it is a very good news because I told you that this K2 allows us to probe the interior of the star. But if it was really sensitive on the mass loss rate prescription, then we would have a problem because what could we conclude? So I think it shows the robustness of the K2 to probe the interior of the stars. But it still doesn't solve our problem. So then I got a bit crazy about that. So I test something a bit more fancy. So you have the reaction rate, the 14 N14 PG in that is the slowest of the CNO cycle, and that is the most critical during hydrogen core burning. So if you have a slower reaction rate, then the H burning process is slower. You have a hotter core and an evolution on the main sequence that happens at higher luminosities. And this is exactly what we want because we have a too low luminosity. So let's try that. So I've seen a paper claiming that the rate should be 10% of NAC2 and that there were high uncertainties on this reaction rate. And what we can see here is that we move from the plane to the dotted line, and we see that we can reproduce the position in the HR diagram. And magically, we can also reproduce the K2 with moderate overshooting of 0.8. But in fact, it turned out that, well, those rates may be underestimated and that there were some errors in the table and so on. So it's definitely not the reason, but it shows you that you have to change a lot those reaction rates to get something that works. So even if there are high uncertainties on this reaction rate, it is not the reason why we cannot reproduce our stars. So the statistical of my GENEC models put to the K2 test is shown here. So you have the different quantities as a function of the overshooting this time. And I also added the nitrogen surface abundance as well as the mass loss rate here. And you can see that we have this K2 discrepancy. We cannot reproduce the K2. And if we increase the overshooting, we see that we get closer to the observational box. But still, it doesn't work. A change in metallicity has no impact. A change in helium maybe, but still doesn't seem to be solving the whole problem. If we have clump binary models and the mass loss rate should be larger, well, it has no change on the K2, so no impact here. And the only way to reproduce the thing is if you really change the N14 PG reaction rate. So the only conclusion I can get from this is that we need a mechanism that slows down the increase of the radius, but I haven't found it yet. Some studies are ongoing in Heidelberg for finding some more, doing more tests. But if you have a solution to that and a magical mechanism to slow down the increase of the radius of the star, I would be very, very happy to know about it. So I promised you that I would show you some evidences of larger convective cores in massive stars. I'm sure you know a bunch of them. So in eclipsing binaries, we have 1D model from Chakenko 2020 here, showing you that here different lines. So from the dash to the dot, you increase the overshooting, and the different colors here, set of colors, is different hydrogen in the core. And you can see that to reproduce the different stars here, you need to go to higher overshooting. There are 2D hydrodynamic models of 3 binaries here with different overshooting. And you see that if you increase the overshooting, you better reproduce the stars, and especially the most massive ones here. There is also lately a study from Mao 2024, which suggested that I have no plot to show you, but they suggested that an overshooting of 0.7 should be expected for massive stars. Then this one, you definitely know the main sequence width in the HRD diagram, that if you go to higher masses, you need more overshooting to represent it. Then you also have asteroseismic gravity mode of single stars. Here it's a pretty old plot, and I didn't find a more updated one, but you can see that if you adopt an overshooting of 0.1 as usually adopted in older grids, then it doesn't reproduce all the stars. You also have clues from the here the HR diagram that to avoid this Unfred-Davidson limit, if you go to overshooting much larger, so here it's even 1.2, then it allows you to avoid this limit. This study I showed you at the beginning, so convective core entrainment in 3 to 1D guided models. And you see that for the most massive stars, you expect a larger overshooting than typical 0.1, 0.2 overshooting. And lately, a 3D non-perturbative modeling of Fele 24, where usually the apsidal motion is considered as a perturbative approach, but here they added the non-perturbative modeling, and there are significant differences on the apsidal motion rate. If we focus on the blue track here for massive star, it has an impact, and this turns out to reflect on an impact of K2, and it increased even more the differences between theoretical and observational K2. Okay, so in summary, the beauty of K2, I think I've shown you that if you have a spectroscopic and eclipsing binary, then we have all the stellar and orbital parameters, and then it's the wonderful world because we can really probe the interiors of the stars. If you have an eclipsing binary, well, we can still manage because photometric light curve can give you a lot of information on the stars. But then what happens if we have a non-eclipsing spectroscopic binary? Because there we have no masses and no radii. So then it's a bit tricky. But there is something that we can actually do using the apsidal motion is to derive the masses of the stars. And that will be the last part of my talk. So let's go back to the apsidal motion equation here. So you see that if you don't have an eclipsing binary, you cannot get the mass of the star and so on. So you cannot really solve those equations. But what you can do is that you can solve them for the mass of the primary, and you assume values for the radii and the K2 from stellar models. So the principle is the following. You assume that both stars have the same age, and you use the mass ratio that you can get from the radial velocities. Then you derive the radii and the K2 of the star from evolutionary calculation as a function of the mass of the primary and the age of the system. So in practice, the method is both model and age dependent, but it then turns out that it can be very reliable. You compute grids of evolutionary models, you construct the different isochrones, and for each one of them, you find a solution of the apsidal motion equation with the only independent quantity that is the mass of the primary. And then you get the value of the mass of the primary that correspond to the age of the isochrone. You have constraint on the mass function that impose a minimum value for the primary mass, but you also need a detached system. The only thing is that as I told you, the Newtonian contribution to the apsidal motion rate, it depends on the radius to the 0.5. So you need accurate stellar models, and don't ask me what accurate stellar models means, but we do our best for that. So this technique has been developed about 20 years ago. And here's a validation by Benvenuto 2002 on eclipsing binaries. So they validate the technique on system where you know all the properties. And you can see that you can fit both stars of every binary. They have 5 of them with the same isochrone. And what they found also is when you plot the theoretical K2 as a function of the observational one, you can also observe this K2 discrepancy. They are mostly consistent, except one that is marginally marginally consistent and 2 that are really not consistent. So then let's apply this technique to a massive binary here. So first in 2002, Arias et al. Detected the apsidal motion rate is in this non-eclipsing binary, but they couldn't derive consistent masses because they made the hypothesis that the system was synchronized. But about 10 years later, Ferrero revisited the system, derived an apsidal motion rate quite high of 12 degrees per year. They assume an age of between 1 and 2 million years. And here, with the values of the angular velocity of the apse and the orbit, they could here derive the masses of the stars. And they have masses that are quite accurate, and they also derive the inclination of the system. And I want to show you this plot in the HR diagram when you can see the position of the 2 stars from the apsidal motion in pink here. And from earlier literature, you have the position of the stars here. And the discrepancy between both is attributed to the cluster distance, which shows you that we really need accurate cluster distances because otherwise we really have spurious result here. And I want also to make the point that the masses that they derive is compatible with photometric masses of stars that are similar O-type stars, but also compatible with theoretical masses from Martin's 2005 calibration. And then about 10 years after, I revisited the system again with new observations and got an apsidal motion rate very much consistent, but a tiny bit lower. And I assume an age a bit higher. So it's not that the stars have taken 0.5 million years in only 10 years. It's just that the age has been revisited. And what I've done here is to compute several evolutionary tracks for different masses. So you go from blue to green, you increase the mass, and here from green to red for the secondary. And we also have different value of mixing. So from the plain line to the dotted line, you increase the mixing. And then following the result I got for other eclipsing binaries before, and usually the mixing that we had for those kind of masses, I could say that this track that I highlight here should be our best fit models. So I got masses for the stars and got also mixing inside the stars. So these are the results I got, also very accurate. And what I did afterwards is that I took those models and combined the primary and the secondary models and took also the error bars on the mass, on the turbulent diffusion and so on, and compute a grid here where I show the theoretical apsidal motion rate for the different combination of primary and secondary models within their error bars. And all those rates are consistent with the observed one within their error bars. And if you go out and take, for instance, for the primary, a model that is less massive, then the apsidal motion rate is not going to be consistent with the observed one. So this shows you, well, there are uncertainties, of course, but it shows you that with the apsidal motion as an additional constraint for the models, you can get more accurate estimate of the masses of the stars. Okay, so my takeaway message, and I hope I have convinced you that the apsidal motion, together with the stellar and binary properties of a double-line spectroscopic eclipsing binaries, allow you to probe the interiors of stars. And the main conclusion is that the standard stellar evolution models usually predict for those massive stars a too low density contrast between the convective core and the radiative envelope of the star. Another very important conclusion is that we need to move on to account for the binarity inside the models, because as you can see here in this plot, which shows K2 as a function of the radius here, you can see that single star models in plain line and the Dutch one really give you different results. So another another conclusion also is that we apparently need larger overshooting inside the models, but still the problem is not solved. So we definitely need to increase the number of systems studied this way to see if it applies to all stars, all mass, and see if we can find more trends than that. And another thing that is also very interesting to investigate is the apsidal motion in non-eclipsing binaries, because in this way we can derive more accurate stellar masses, which are of course model dependent, but this is better than nothing. So my future project now, the thing I want to do is that first I would like to establish a benchmark sample of massive binaries with well-constrained apsidal motion rate over a very wide parameter range. And I have selected already more than 40 binaries, so I just need to analyze them. And then I would like to build tailored binary models to those stars to reveal the efficiency of mixing inside those models, but also derive the convective core sizes of those massive stars as a function of mass, but also as a function of age and evolution on the main sequence. And then after that, there are many things I want to do, but one of that is that I would like to exploit the complementarity between apsidal motion and asteroseismology in massive binaries that contain beta-Cepheid variables. And after that, why not computing grids of binary and single star models with the same physics based on the result of the previous objectives, and see when tides play a critical role, but also apply the apsidal motion in non-eclipsing binaries to get more accurate evolutionary masses, and then interpret Wolf-Rayet and supernovae 1BC in terms of single and binary star evolution, and much more. But I think that for now I will I will stop here and thank you for your attention, and I will gladly take questions.
Thank you very much, Sophie. And by amazing future project you have ahead of you. So hopefully you will find soon the chances to continue working on it. Now it's time for a question, but before I want to say that I'm really glad that you had the opportunity with this longer talk to really explain details in the results, but also in the basic, because it has been more easy to follow some of the things you've been explaining. So I think this is great, and thank you very much. And I'm going to use my privilege as a host to ask the first question. I'm curious because at some point you were mentioning that you were playing with the helium abundance.
Mm-hmm.
For me, as a spectroscopic, helium abundance is the surface abundance. But in your case, what is for you the helium abundance when you model the interior of the star, or in this case, what you
The,
refer with this
the
helium abundance?
It is the initial helium abundance of the star, like the metallicity. So it's really the content of the star as it's when it starts its evolution.
So is this the starting helium abundance of the whole star is not necessarily because the helium is not the same in the core and the surface and everything. It's like the initial helium composition,
E-
let's say.
exactly. Yeah, I should use composition. Yes.
Okay. Thank you very much. So if anyone wants to, yeah, we have Gloria, for example. Go ahead when you want.
Yeah, thank you so much for that wonderful talk. It really gives a great overview of what one can do with all of these variables. The one thing I missed was how do you deal with the internal velocity structure? Are your models always rigidly rotating? Is that based on the assumption that stars become rigid rotators very quickly, even in binaries?
No, so the magnetic model do rotate rigidly, but the advector diffusive scheme that we adopt for the angular momentum transport sets the star on a differential rotating structure. So we have the core that is rotating faster and the surface that is rotating slower.
But during the, sorry, in the case of the binaries,
Mm-hmm.
uh, let's say that the surface synchronizes with the binary period sooner than the interior.
Yes.
So do your models include that in fact effect, and is that relevant at all, or is it not relevant?
I'm not sure I understand your question. So here, I will try to answer. So the surface is synchronizing with the orbital motion. So
Yes.
in the advector diffusive model, what we have is that the surface velocity is the same. Well, the angular surface velocity is the same as the orbital one, but then the core is rotating faster.
Yes.
In
Okay.
in the magnetic model, we have a flat profile of omega as a function of the distance from the core of the star. So here we have synchronization of the surface also, but a flat omega, while the advector diffusive, you have a decreasing profile.
Okay. Perfect. Yeah. That's what I was intuitively assuming. So you can have a pretty strong velocity, angular velocity gradient within the star.
Yes, in the advector diffusive model, yes.
Exactly. Okay. Thank you.
Any other question? Meanwhile, people is thinking about questions, I'm going to ask you. This is just curiosity because when you were mentioning the different methods, one of the things we always assume is that in the binary, both stars have the same age. But then
Mm-hmm.
I was thinking, okay, in the models, you consider that the zero age is the sums. But then if you have stars with different masses and taking into account that the contraction phase is different, so not necessarily they have when you how is H in this case? Is about binaries, not really related to what you say, but I'm curious.
Uh, well, the problem here it's not really a problem because what we model actually when we model binary star in GENEC is that we model one star. but we take into account the secondary by assuming it is a point-like particle. So we don't evolve the secondary star. So this is not really a problem because it's just a point that is at a certain distance with a certain orbital period on an orbit with a certain eccentricity that is point-like. So it doesn't evolve with time. So it's not, but I get your point indeed. And then I don't know how we will model that in the future, but that's something that we will have to
Yeah, but
take
I
into
assume
account.
this is only important if the difference in the masses of the two stars is really large, no? If they are similar masses, basically.
Yeah, and also here the system that I show you is a twin system, which means that here the two stars have exactly the same masses, so they are defined by the same model. And here in this case, GENEC can account for the mass loss rate of the secondary. So the mass of the secondary was evolving as the mass of the primary. It's just that it was not evolved in detail. It was still a point-like particle. But yeah, that's something we will have to think about.
Mhm. Okay, thank you. Any question, the people? If not, maybe my last question. You already have a nice compilation of binaries where you're going to be working on. Do you think this number will be enough, or is you already know that this will be the first step, but then it will be better to have many more stars covering a broader range of masses or mass ratios? Or
Well, here the system I have, they already cover masses from 8 to 60 solar masses and period from 1.2 to 35 orbital period, eccentricity from almost, well, a bit almost 0.02 until 0.62. So I think I cover a broad ranges of everything. But that's true that it would be better to have even more system. The only problem is that for now, if I want to start now, only I think I have those system because I need spectroscopic observation taken for a very long period. I also need light curves and so on and so forth. And also the system have to have the orbit has to have an inclination that is close to 90 degrees for the eclipses to be observed. So there are several constraints for that. But I have also other system in mind, and I would like first to acquire new data for them and make sure I can cover the orbital cycle. And to answer your question, we will see. I think that with 40 system already, we will see if a trend is going in convective core masses, if we have a trend in internal mixing efficiencies and so on. And then with this first sample, I will see if I need more or if with that we can already conclude a lot. And I've also the plan to extend to the LMC and the SMC to see if there are differences with different metallicities. And there are more systems because we don't have the problem of extension towards the galactic plane.
Mhm. Yeah, okay. But then you need a really long time span also for this observation and
Yeah, there are accurate estimates. There are accurate light curves already, so we could derive the Apsidal motion rate from the light curve as it is done in ZASH 2020 and Hong 2016, and complement with the radial velocities. Maybe not to get the Apsidal motion rate because the time span is shorter, but we could get the other constraint from the radial velocities.
okay. So then last chance for people to ask question to Sophie. If not, you always have her to ask by mail. So then thank you very much, Sophie, for this very nice talk and everybody for joining. And see you in 1 month in the next. Gloria, maybe want to say something? No? No. Okay. Perfect. So thank you and see you soon.
Thank you.